So we have strength of materials practice final exam part 1. So let's begin here. Number 1, a vertical steel rod of length L equals 1.8 m is fixed at the top. The cross-sectional area varies continuously according to A of x equals A naught times the quantity 1 plus x over L, where A naught equals 450 mm squared, and x is measured downward from the fixed end. Tensile force P equals 90 kN acts at the bottom. So for letter A, derive an expression for the normal stress distribution sigma of x. And part B, derive the total elongation of the bar. For part C, if E equals 210 GPa, compute the elongation. And for part D, compare the result to the uniform rod with area A naught. So this is an axial loading in a non-uniform bar problem. So A of x equals A naught times the quantity 1 plus x over L. The internal axial force is constant. N of x equals P. And stress equals a sigma of x equals P over A of x equals P over A naught times the quantity 1 plus x over L. The elongation is delta equals the integral from 0 to L P over E A of x dx. Delta equals P over E A naught times the integral from 0 to L dx over 1 plus x over L. Here when we integrate, we can let u equal x over L plus 1, and dx is going to be equal to L du. So we have delta equals PL over E A naught times that integral from 1 to 2. And this is du over u form. So this is just going to be delta equals PL over E A naught ln of 2 when performing the integration. And part C, P equals 90,000 and L equals 1.8 m. E is 210 times 10 to the 9 PA. So A naught is 450 times 10 to the negative 6 m squared, and then just substituting delta here equals 90,000 times 1.8 times 2 divided by 210 times 10 to the 9th times 450 times 10 to the negative 6, we get 1.19 mm. And for part D, for a uniform rod of area A naught, delta sub uniform equals PL over E A naught. So delta sub uniform is 1.71 mm. So delta divided by delta uniform, that would be ln 2, which is approximately 0.693. So we could say that the tapered bar elongates about 69.3%, as much as the uniform bar A naught. Okay, moving along to number 2. See if this holds. Okay, so number 2, a rigid plate is suspended by 3 vertical rods. Rod 1, aluminum, is aluminum, length L, area 2A, modulus 70 GPa. Rod 2 is steel, length L, area A, modulus 200 GPa. Rod 3, brass, length L, area 3A, modulus 100 GPa. So it says here a downward load F is applied at the center of the rigid plate. Okay, for A, B, C, D, respectively, formulate compatibility conditions, determine the force carried by each rod, determine the displacement of the rigid plate, and if the steel rod yields first at 250 MPa, determine the maximum allowable external load. Okay, so this is a statically indeterminate axial system. So what we could do here is assume the load is centered and the rigid plate remains horizontal, so that all the rods have the same displacement, where delta sub 1 equals delta sub 2 equals the delta sub 3 equals delta. For each rod, F sub I equals K sub I delta, where K sub I equals A sub I, E sub I over L. And the rod stiffnesses here, total stiffness, what we can find here, K sub 1 is 2A times 70 over L is 140A over L. K sub 2 is A times 200 over L, 200A over L. K sub 3 is 3A over 100 over L equals 300A over L. So our total stiffness from adding these up, K sub total, is 640A over L. From there, equilibrium gives the F equals F sub 1 plus F sub 2 plus F sub 3. So F equals the quantity K sub 1 plus K sub 2 plus K sub 3 times delta. And what we're going to get here, delta is FL over 640A. So F sub 1 equals K sub 1 delta. F sub 1 equals 140A over L times FL over 640A. So F sub 1 is 140 over 640 times F, which is 0.21875 F. F sub 2 is 200 over 640 F, so that's 0.3125 F. F sub 3 is going to be 300 over 640 F, which is 0.46875 F. So the plate displacement is going to be delta equals FL over 640A. And for the steel yielding first, sigma sub 2 equals F sub 2 over A. Sigma sub 2 equals 0.3125 F over A. From here, what we could do is set sigma sub 2 equal to 250 MPa. So 0.3125 F over A equals 250 MPa. F equals 250A over 0.3125. So F sub max equals 800A, where A is in mm squared if the stress is in N per mm squared. So we could say here our F sub max is 800A N if A is in mm squared. Okay, moving along now to number 3. So at the point in a structural member, stresses are sigma sub x is 120 MPa, sigma sub y is negative 40 MPa, and tau sub xy is 55 MPa. So part A, derive the transform stress equations for a plane rotated by angle theta. Part B, determine the principal stresses. Part C, determine the principal plane orientations. Part D, determine the maximum shear stress. Part E, construct Mohr circle analytically. And part F, if failure follows the Tresca criterion with yield strength 300 MPa, determine the safety factor. Okay, so this is a stress transformation and principal stress problem. Okay, so part A here, sigma sub x prime equals sigma sub x plus sigma sub y over 2 plus sigma sub x minus sigma sub y over 2 times cosine 2 theta plus t sub xy sine 2 theta. And sigma sub y prime equals sigma sub x plus sigma sub y over 2 minus sigma sub x minus sigma sub y over 2 minus tau sub xy sine of 2 theta. So, and tau sub x prime y prime equals negative this quantity sigma sub x minus sigma sub y divided by 2. Sine of 2 theta plus tau sub xy cosine 2 theta. For part B, the average stress is sigma sub AVG equals 120 plus negative 40 over 2, so that's going to give you 40 MPa. The radius of Mohr's circle, capital R, equals square root of that quantity, sigma sub x minus sigma sub y over 2 squared plus tau sub xy squared. So capital R is going to equal the square root of 80 squared plus 55 squared. So capital R is going to be the square root of 9,425, which is about 97.08 MPa. So our principal stresses for sigma sub 1 is sigma sub AVG plus R. So sigma sub 1 is 137.08 MPa. And sigma sub 2 is going to be sigma sub AVG minus R, so sigma sub 2 is negative 57.08 MPa. And going to number 3, determining the principal plane condition. So the principal angle here, we have tangent of 2 theta sub p, that's going to equal 2 tau sub xy divided by sigma sub x minus sigma sub y. And tangent to theta sub p, that's going to be 110 over 160, which is 0.6875. And 2 theta sub p, that's 34.51 degrees. So theta sub p is about 17.25 5 degrees, or 17.25 about degrees. Part D, or maximum in plane shear stress, tau sub max equals R. That's going to equal 97.08 MPa. For part E, our Mohr circle, our center here is 40 MPa, and our radius is going to be 97.08 MPa. And for the Tresca criterion, it's going to be sigma sub 1 minus sigma sub 2. That equals 194.16 MPa. Our n is sigma sub y over sigma sub 1 minus sigma sub 2. So n is 300 over 194.16. So n is 1.55. Okay, so that's the first part. Thank you very much, and have a great day.